Hey, Gibson here. Today we're going to move on to the next topic in our unit on light and talk about reflection and refraction. So let's look at our objectives here. So the first is for you to be able to explain the law of reflection. Okay, pretty simple once we get to it. And then the thing that's a little more challenging to wrap our heads around is this concept of an image and where the image will form when we're looking at an object in a plane mirror. Okay, so more to come on that. And then we'll move into refraction. We'll define what refraction is, what causes it, and then be able to answer a variety of different questions and solve problems using this concept of refraction. So if you remember at the beginning unit, introduction into the fundamentals of light, we talked about different behaviors of light. And a lot of them that we're going to study are all about why does light, or how does light change direction. So these are two methods, reflection and refraction, that cause light to change its direction. Okay? And we're going to stick with the wave model of light here with light rays to be able to understand how both of these behaviors work. All right, so let's talk about reflection a little bit. And the key concept here is that if we want to look at an object, we have to look along what we call the line of sight. So in order for us to see an object, we have to look along the path that the light is traveling when it reflects off of that object, okay? Now, whether that's the light source itself, right? If we look straight at a light bulb or something, then that's pretty obvious. But if we're looking at an object that doesn't generate light, but rather reflects it, then we have to be looking along the path that light takes when it shines on that object, reflects off the object, and then into our eyes. Okay, so let me show a little diagram if I can just sketch this here. Hopefully it won't make a big mess of this. But if we were to start, let's see, start here, right? The light ray basically comes this way, right? Hits Yoda, and then it's going to reflect off of Yoda. Now, this should be a straight line, but I can't obviously do that very well with my little pin here, okay? But basically, that's what we mean by line of sight. We have to be looking along that straight line that the light ray is going to travel, okay? So let's see, I wanted to clear that. There we go. All right, so let's formally define what we mean by reflection. So reflection is simply the bouncing back of a particle or wave that strikes the boundary between two media. Okay, so reflection occurs anywhere you have two different media that come together, and it's right at that boundary between the two media that the reflection actually occurs. Okay, so let's look at some examples. The most common is a mirror, right? We use mirrors almost every day. Get up in the morning, look in the mirror in the bathroom, right? So if you really look carefully at how a mirror is constructed, the light ray is traveling through air, but then it travels through a piece of glass. Now, on the back side of that glass is a very thin layer of metal that's been deposited down on that glass. If you turn a mirror sideways, you can kind of see it. Or if you look on the back, right, you'll see kind of a black coating, but it's actually some type of metallic coating. The best mirrors are made with silver because silver is highly reflective, okay? So what happens, of course, is the light ray, right, comes down, and right at the boundary between glass and metal, it reflects back, okay? So we call that full reflection, where all of the light energy is reflected back. None of it passes through the metal or the mirror in this case. Some of that energy obviously would be absorbed. So a good mirror will reflect, most of the energy. Now we can contrast that with other types of reflection. So say between air and water, if you've ever swam in a lake or a swimming pool, you realize that, yeah, light shines off the surface of the water, right? That's where the glare comes from. But also, if you go underwater, you can still see, right? So clearly, a lot of that light has to be traveling through the water, right? When we talked about transparency, so water is transparent to light. So here's what it would look like, right? Some of that energy is going to get reflected, some of it's going to continue to travel through, and we would call that partial reflection. All right, so that's the basic definition. It can be full reflection or partial reflection. So here's the basic principle for how that light is going to reflect, and it's really a geometry definition. It says the angle of reflection for a wave that strikes a surface is equal to the angle of incidence. Okay, so angle reflection equals angle incidence. Now, let's kind of define what we mean by angle of reflection and angle of incidence. And this is really important because we're going to kind of use these definitions not only in reflection, but in refraction. Okay, so let's say we have a reflective surface here. Here's our mirror, right? And we have a light wave that is coming in. So if it's the ray that's coming into the surface, we call that the incident ray. Okay, so that's a key term here. Let's see if I can get my highlighter. It's not popping up. Okay. The ray that is reflected bounces off of the surface. That one makes a little more sense, right? It's simply called the reflected ray. Now, the key in terms of defining these angles is that we're going to construct a line called the normal line. And the normal line is a line that will always be perpendicular to the reflecting surface, or the boundary between, in this case, glass and the metal in the mirror. Okay, and the reason that normal line is so important is because the angles will always be defined as the angle between the normal line and the light ray, so either the incident ray or the light ray. So let's add those in here. Here we would define the incident angle as that between the normal line and the incoming light ray. Okay, it's never defined between the surface and the light ray, although we know by geometry, right, those two have to add up to 90 degrees. We can actually use that to help us solve some of these problems. The angle of reflection, same thing, always measured from the normal line. Okay, so we see that coming off of the reflected surface, and the angle is always with respect to the normal. Now, what the law of reflection says is that these two angles will always be equal to each other. Okay, if we're reflecting off of a smooth mirror, they're going to have the exact same angle. So big idea here, angle in equals angle out of a reflective surface. Okay, so law of reflection. All right, so let's just see if we can apply this a little bit and first be able to identify, right, what the correct angles are based on what we just talked about. So in this example, which angle is the angle of incidence? Which one would be coming in? Okay, so remember, it's always with respect to the normal line. Let's put some notes on here. Okay, so here is our, let's see if I can get my pen going. Yeah, here is our normal line right here, right? So where's my incident angle? Well, the little arrow tells us that it's coming in, right? So the angle will always be between the normal line and the incident. So how would we answer that? It would be angle B, okay? Let's see, I guess I have to stop. There we go, angle B. So which would be the angle of reflection? Again, from the normal line, this time to the ray coming out. So that would be angle C. Okay, so it's really important you're able to identify these angles. What are the incident angles and the reflected angle? All right, so another little question here. If we were to apply this concept of law of reflection, we shine this flashlight beam, say a narrow beam, onto the mirror surface. Which of these cards would be illuminated by our flashlight? And let's assume our flashlight beam is nice and narrow, and it's not going to spread out any further. Okay. Well, how would we do that? Well, let's construct our normal line here. Okay. So let me go back and add some lines here. So our normal line, right, is going to go, and I'm going to try and draw this best I can. Oh, terrible normal line. Okay, that's my straight line. but it's perpendicular to the surface. So our incident angle, right, would be this angle right here. So law of reflection says we have to have the same angle being reflected, okay? Like so. So if we were to be able to draw this a little more accurately with a ruler than what I've done here, we would see that this light ray should reflect off at the same angle that it came in and be able to illuminate a card that has a B on it. Okay, so let me clear these drawings and see what that looks like here. There we go. There's our normal line, and here's our reflection. And notice the angle in equals the angle out. Okay, so that's the concept of law of reflection. Angle incidence equals angle of reflection. All right, so let's apply it to a little more complex problem. If we had three mirrors that are mounted at an angle here, each of them with a 45-degree angle to the horizontal mirror, okay, to that surface, and we have a light ray that comes in at a 45-degree angle, could we draw in the path that the light wave would take? And then how many times would it reflect off of these three mirrors? So the process we're going to use is always first establish our normal line. Okay, so let's do that. Here's a normal line that's perpendicular to that first mirror. We draw it right where the light ray is going to hit the mirror. And the incident angle would be, again, between the normal line and the incident ray. Well, we know that the total between the mirror and the normal line is 90 degrees. So if one side is 45, the other has to be 45, right? They're going to add up to 90. Okay, so that's our incident angle. So our reflected angle would have to be the same amount, 45, okay? So if we could get a protractor or a ruler and draw and measure these angles correctly, right, this is what it would look like. So here would be the first light ray reflecting. So now it hits the other mirror. So again, we're going to put in our normal line, draw our 45-degree angle to it that shows now the incident angle, and then show our reflected angle is going to be also at 45. Okay, so if you had three mirrors like this, connected at a 45-degree angle, each of them, and the light came straight down to it, it actually is only going to touch two of the mirrors, and the light's going to come right straight back in the opposite direction that the light beam came in. Okay, now with a normal flashlight, you wouldn't be able to observe this, but if you used a laser, it would be very easy to see that this would cause the laser beam to reflect a full 180 degrees right back in the same direction that it came from. Okay, so kind of a simple example of how we can apply this law of reflection. Let's look at another problem similar to this, okay? What would be the final angle of reflection? So how is it going to reflect off the second mirror here? So again, put in our normal line. Now, what is this angle going to be between the normal line and the light ray? Well, they have to add up to 90, right? So if we have this angle of 30, the incident angle is going to be 90 minus 30, or 60 degrees. All right. So that means our reflected angle has to be 60 degrees, okay? So we can draw that in here. So this point, right, is where if you could draw this out on a piece of paper, with a protractor, you could measure and draw these angles accurately, okay? So, but here's what we know, right? We know that this angle on the other side of the reflected ray has to be 30, right? 60 plus 30 equals 90. And then, therefore, these opposite angles here have to be equal to each other. This would be an isosceles triangle, right? Think about a little bit of geometry here. So therefore, our new incident angle to the second mirror would be 60. Therefore, our reflected angle has to be 60, okay? So in this case, where they're 30 degrees apart, it's not going to get reflected in the opposite direction, 180 degrees, right? It's going to be at a different angle than what it came in at. All right, so that's the basic concept of the law of reflection. Angle in equals angle out, and we always measure to the normal line. The other topic we're going to talk about is this concept of the object and an image, okay? So the object is the real thing that we're trying to look at in the mirror. The image is what we actually see when we look into the mirror. Because when we're looking at the mirror, at the reflection of something, we're not seeing the real thing, right? If it was the real thing, we'd look straight at it. But if we're looking at it as a reflection in the mirror, we call that the image, okay? It's not the same as the object. The object is the real thing. The image is what's formed in the mirror, okay? So let's look at how that works. How does that image get formed and where does it get formed, okay? So to do this, if you have this at home, you could try this, right? If you have a little pocket mirror or something, but we're gonna set a mirror down on a kind of invisible line here. And in front of that mirror, I'm going to put an object like a pencil. Okay, so you could do this if you have a little mirror in home. You'll need a second pencil, I would ask you to get. But if we set that pencil in front and then kind of move our head down so we can see that pencil reflected in the mirror, where would the image actually be? Well, we can locate the image by placing another pencil behind the mirror, but it's tall enough where we can see it over the top of the mirror. And we want to move that around until it lines up exactly with our image in the mirror. Now, what do I mean by line up? Let me draw a little bit on here. We want this part of the pencil to line up with the image that we see in the mirror, right? Here they should line up straight up and down. And then if we have this pencil behind it in the right location, no matter where we move our head back and forth to look at the image in the mirror, they should stay lining up. Now, if they don't do that, as you move your head back and forth, you don't have the pencil in the right location. So you got to move the pencil around until when you move your head back and forth, it always stays lined up. And there is a location where that will happen. You might have to play around with that a little bit. Okay. So once you do that, we remove the mirror here. Where we place that pencil is where the actual image, not the object, but the image, remember the image is not the real thing, it's the reflection that we see in the mirror, but that's where it would appear to be when we look into the mirror. Now, we can't touch an image, right? It's kind of this virtual thing we see in the mirror, but we can figure out where it appears to be located, right? And that's what we've done through this process here. Now, here's some key findings. The image will always form an equal distance, but on the opposite side of the mirror, okay? So if this pencil was 5 centimeters in front of the mirror, the object was, then the image will be 5 centimeters behind the mirror, okay? So this is the rules for where the image forms. It will always form the same distance behind the mirror that the object was in front of the mirror. So why does it do that? Let's use this light ray model here to see where this image forms. And we're also going to apply the law of reflection, okay? So here's my eyeball down below this bird, but I want to look at the bird through the mirror here, okay? So if different parts of the bird, right, are going to cause this light ray, how will that light ray reflect back to my eye? Well, it's going to have to follow the law of reflection, right? So these rays are going to come back this way. Now, let me just draw in, I can do this fairly neatly here, and we'll do it in black this time. Where would we put our normal line, right? We have a normal line like this between each, I'll just draw it solid, between each incident ray and reflected ray, right? So this angle has to be the same as that angle, okay? So you can see how I put these red light rays on the screen. They all tend to match up with what we know about the law of reflection, right? Those angle in have to be angle out, okay? So that's, these light rays will reach our eye and we can see the bird here. Now, why are we doing this? Remember, the whole reason we're doing this is to understand where the image forms using the ray model. So here's how it works. If we were to take these reflected light rays and extend them back beyond the mirror, we'll find that they will come together. And the word you'll hear me use is converge, okay? Converge means to come together. So these rays would come together at a single point, and at that point is where the image would form. Okay, so again, if you look at how far the bird was in front of the mirror, the object, you can see it formed at a equal distance on the opposite side of the mirror. But we can use this ray model and the law of reflection to actually locate that exactly. Okay, so the geometry kind of supports the rule here. So just to formalize, image in a plane mirror in our definition down below here, the image position, we'll call that DI, is equal to the negative of the object position, and negative indicates that it's virtual and on the opposite side of the object. So whatever DO equals, that's going to be the same, but we'll use a negative for DI. The other thing that happens is that for a normal flat mirror, plane mirror, the object height or size will appear to be the same. Okay, now you've all probably noticed kind of mirrors that are curved, either in or out. The object size changes a lot when you look at that, right? But if it's a nice flat mirror, we call plane mirror, then the image height and the object height will always be the same. Okay, so those are kind of the two rules for how the image forms. All right, so let's apply this in kind of an interesting exercise here. Who can see whom? Okay, so here's our mirror. We've got what, 7 people down below here, A, B, C, D, E, F, G. And for each person down below, could we figure out who can see whom, right? So which other people could person A see if he looked in the mirror? So how could we figure this out? Well, let's start to apply our rules here, okay? So we know first that the images, right, for each of the real objects down below will form an equal distance on the opposite side of the mirror. So let's go ahead and locate where these images would be. So the D object, right, would be, or the image rather for D is going to be the opposite side of the object for D. So we can put all of these, right, just the same distance on the opposite side of the mirror. Okay, now we can begin to draw our light rays. So if we want to say first, who can A see? Well, if A were to look in the mirror, right, they could see object G, because notice the line that we've drawn has to obey the law of reflection. Let me go ahead and sketch in our normal line again here. Okay, so I'll do it in red this time. So here's our normal line, right? So this angle here has to be equal to this angle here, okay? So when we use the law of reflection, it says that light ray has to hit the mirror right at this point that I'm kind of coloring in here with my red circle. So if it travels through that point, if we extend it beyond, right, we are going to be able to see object G, okay? So we would be able to see object G in the mirror. So let's try the rest of them here. How about F? Yep, looks like we could see F. How about E? Yes, we could see E. How about object D? Well, E or B, I'm sorry, D, C, B, or A, we won't be able to see them in the mirror because the line of sight that we would have to the virtual image does not pass through the mirror, right? And therefore, we're not going to get a reflection of that. So in this case, person A, they could see E, F, and G, but they're not going to be able to see B, C, and D, the people right next to him. How about for person E now? Just see if you can take a minute. I'll pause here and figure out who could E see. If you can just kind of at least use your finger or a pencil on the screen here to figure out which ones would be visible in the mirror. Okay, got it figured out? All right, so same thing. Let's start with E to G, nope. E to F, nope. E to E, yes, of course you'd be able to see yourself looking straight into the mirror. E to D, yes. E to C, yes. E to B, yes. And E to A, yes, just barely, right? It's going to catch the edge of the mirror here. So it's really just objects E and F that she would not be able to see, or F and G rather, she would not be able to see. Okay, so kind of a little puzzle here that we can use the law of reflection to solve. All right, So that does it for reflection. Let's shift gears now and talk about refraction. Again, this is the bending of light. And there's a couple things you can probably do at home. You maybe have already done this and noticed it, but where you can observe this phenomena of refraction. So here's a real simple one. Take a clear glass, fill it full of water, and then just drop a pencil into it, okay? But do it two ways. The first time is just put the pencil in right straight up and down vertically, okay? And then tilt it over to its side like it's shown in the glass here. What do you notice? Well, it looks like the pencil is bent, or there's actually a break, right, between the real object and then what we're seeing as far as the refracted light inside the water, okay? That's caused by the bending of the light as it travels from the water through the glass and then back to the air in order to reach our eyes, okay? So we'll talk about this a little more, but this is a simple example of what refraction is, okay? Here's another thing you can do. Take a piece of paper and kind of in its tall direction, just draw two big arrows, one in each direction, okay, but near the bottom. And then what you're going to do is take a glass. You can use that same clear glass you used before. And before you put anything in it, dump the water out, just put it in front and look through the glass at those arrows, okay? So they should look pretty normal in their direction. But now, go ahead and fill up the glass, but first just fill it up so it just covers the first arrow. And what do you notice? Okay. And then go ahead and fill up the glass to cover both arrows. And then what do you notice about the arrows? Did they change their size? Did they change their direction? Okay. So again, we're getting the light of the image of the arrows traveling through the glass, through the water, back through the glass, and then into the air to our eyes. So each time it changes from one medium to the other, it has an opportunity to refract, right? Change its direction or bend. And in this case, you see it quite drastically, right? The arrow actually flips around. Now, why does it flip around? Well, what you've basically formed with this glass of water is a lens, like just like the lens in our eye or a lens of a magnifying glass. And if you've looked through lenses before, sometimes you'll notice that they actually cause the image to reverse itself. And that's what we're seeing here. Once we get through this lesson on refraction, we'll actually see how does the principle of refraction used to make something like a lens, right? And we'll look a little bit at lens behavior. Okay, so a couple things you can do there to be able to observe, hopefully at home, this phenomena of refraction, the bending of the light. So why does it bend? Okay, why does light bend? Well, we're gonna start with a analog model here, and then we'll shift over to light. But let's say we had an axle with two wheels on the end of it, okay? And the whole thing is glued together solid. So if the wheel turns on one end, it has to also turn on the other end here, okay? So the whole thing is one big piece. Now, if we were to roll that axle from a smooth sidewalk onto a grass, what happens? Okay, you guys maybe have done this on your bicycle when you were little, right? You slow down when you hit the glass, or grass rather, okay? So let's let that happen. Whoops, let me back it up here. Here we go. Wait a second, why? Let's try this again. Should be, and there goes my animation. Okay, so it hits the grass and slows down, but notice because both wheels hit the grass at the same time, they both slow down and it continues along that straight path. So think about that pencil you put in a glass of water when it was straight up. You didn't notice any bending of the light, any refraction. Same case here. Okay. Now let's try it if the wheels hit the grass at an angle. Okay, so as it travels, the bottom left wheel is going to hit the grass first, and it's going to slow down first, while the other wheel is still traveling fast in the sidewalk. Well, what happens? Let's see, right? That inside wheel hits the grass, so it actually changes its direction. Now, once both wheels get on the grass, they're now traveling at the same speed and they continue on in a straight direction. But notice the direction changed when we went from the sidewalk to the grass. So when we went from fast to slow, it changed direction. It actually moved towards our normal line. Okay? Here's our normal line. So the actual change directions as it crossed the boundary between two medium that had different speeds. Okay, now if we extend this model to waves, all waves, whether they're water waves, sine wave, or sound waves, light waves, they also bend when one part of the wave is made to slow down or speed up and become faster than the other part. Okay, so this is what is the basic cause of refraction, the changing of speed as the wave moves from one medium to the other. So here's our official definition. The change in direction of a wave as it crosses the boundary between two media in which the wave travels at different speeds. So let's look at this again from a wave model. Here we have two mediums and the waves traveling through it. Let's think of these dark or light bands as the wave fronts, right? So you could think the dark is the crest and the white is the trough. Picture the wave moving in. So you can see the distance, right, between the waves for medium 1. Now let's draw that same thing in for medium 2, right? Notice the waves are closer together and they've also changed their direction. Okay? So if we were to draw a ray rather, that's perpendicular to those wave fronts, here's what it looks like, right? We've got the incident wave coming in medium 1 in blue. It hits the boundary between the two materials or medium, and it changes direction. So remember from our example of the sidewalk to the lawn, right? As it slowed down, it moved closer to the normal line. So same thing happens here in terms of wave behavior. As it slows down in medium 2, it's going to bend towards the normal line. Okay, so we go from a faster to a slower, it moves towards the normal line. Now, here's an easy way to conceptually test which way is the light wave going to move. Okay, so if we go from faster to slower, I call this the pencil test, right? Here's our light wave coming in. So now the question is, as it crosses that boundary, is it going to bend closer to the normal line or further away from the normal line? Well, we use a pencil test. So pencil, think of that as our axle with the wheels on it, right? So if we slide our pencil along the light ray, the sharp end of the pencil, right, hits the slower material first. So it's going to slow down while the other end keeps traveling fast. So that's going to cause our pencil to turn. Let me show it one more time here. Okay, so it slows down, the other end keeps going. So that causes it to bend closer to the normal. Okay, so faster to slower, it will always bend closer to the normal. Now, how about slower to faster? What will happen? Well, same thing. Let's use our pencil test. Okay, so now it's going to hit the faster first, which causes the sharp end of the pencil to turn, and this is going to move us away from the normal line. So here's the big concept, right? Slower to faster, it will move away from the normal line. Okay, so the amount that it refracts or bends is always defined as the angle from the normal line. Okay, so let's ask this question a little differently here. Here's the incident ray coming in through material B. It hits the boundary and then bends towards the normal line for material A. So which media is faster? Well, what would have to happen if we use our pencil, right? If we use our pencil, in order for it to move towards the normal line, it's going to have to slow down when it first hits A while the other end is still in B. That's going to cause it to move towards the normal. So in this case, A is slower than B. So how does all this work with a light ray and common materials like air and water? Okay, this happens just about all the time. And if we look around, right, we can find this boundary between air and water. So here comes our light ray. and it hits the water and it bends. Now, it bends, notice, closer to the normal line, which is telling us what? Where is light going to travel faster, in air or in water? Well, in this case, it's moved closer to the normal line, so that means it's going to be moving slower in water. Okay, so we'll talk in a minute about what actually causes light to slow down when it moves into a material, but in this case, it's always going to move to the slower or towards the normal line if it's slower. Let's do the opposite, right? We're going from water to air, we're going from slow to fast. So the light ray is going to move away from the normal line. It's going to bend away from it. Okay, so same thing we've been talking about, just defined now as a boundary between two specific materials, air and water. So let's talk a little bit more about the speed of light, because you might say, wait a minute, I thought the speed of light is constant, right? 3.0 times 10 to the 8th meters per second is what we have been using in the first lesson on fundamentals of light. And we've always been told nothing can ever go faster than the speed of light. That's true, okay? But remember, this is the speed of light in a vacuum, okay? In the vacuum of space. And it turns out in air, it's pretty close to a vacuum. It slows down a tiny little bit, but not much, okay? We can kind of assume that it's traveling at this 3 times 10 to the 8th when it's in air. But why does it slow down significantly when it goes into materials such as a glass of water or glass material? Let's see if we can understand this. Watch a little video here.
We all know that light bends when it travels through glass, water, or other transparent material. That's how a microscope, lighthouse, and spectacles all work. And you might even know that light bends because it travels slower through glass or water than through air. But why does light slow down? And how does it speed up again when it comes out on the other side? There's nothing there to give it a push. Well, if you think light is a wave, it's easy to explain. Electromagnetic waves simply travel slower through glass than through air. So the wave crests are closer to each other, but the light still oscillates the same number of times per second. It stays the same color. When the wave hits the air again, its color still doesn't change, while the crests spread out and it returns to light speed. The simplified explanation is that the energy of a wave is determined by its frequency or color, which doesn't change. So it doesn't need a boost to speed up at the other side. But wait, you say, I thought light traveled at the same speed in every reference frame. You still haven't explained how it can slow down. Well, now let's think about light as a particle. When light goes through glass, it gets knocked around and bumps into all sorts of molecules and electrons. So whenever it's traveling at the speed of light. But it's busy interacting with and scattering off lots of stuff along the way, and it doesn't necessarily take the shortest path through the glass. It's like the President of the United States trying to cross a room. If the room is empty, he can walk across directly. But if the room is full of people, all of whom want to shake the president's hand, even though he walks from person to person at full presidential speed, he'll get slowed down along the way. As soon as he reaches the far side of the room, though, he's free to resume his pace. Full speed ahead, Mr. President. We all.
Okay, so hopefully that video helped a little bit. I like the analogy of light as a particle. I think that's easier to understand in terms of why it slows down. So let's look at that again, right? And the wave model, it depends, the energy of a light wave depends on the frequency or color of the light, and that will be constant. The light color is not going to change as it moves from one medium to the other. What will change, right, is the wavelength. It will become shorter, therefore the wave speed has to decrease. Okay, so that's kind of the wave model explanation. The particle model, again, I think is a little easier to understand. They move at full speed between kind of collisions or encounters with atomic structures, right? So here comes our light wave in. If it's going to be transparent, remember these are not going to oscillate at their resonant frequency, but rather regenerate the light energy. So that absorb and regenerate, and as it bounces around from one atom or one molecule to the next, is what gives it a longer path to travel, but it's still going at full light speed between those structures, but the net effect is that it's going to take longer, right, for it to pass through the atomic structure of a medium, and that's what slows it down. Now, how do we describe the speed of light through other materials besides a vacuum? We use this definition of the index of refraction, and it's simply the ratio of the speed of light in a vacuum, and we'll use C for that, right? That's the symbol we use for 3 × 10⁸, divided by the speed of light in the medium. So that ratio of light speeds gives us this constant, or index of refraction. Now, it doesn't have any units of measure because we've got meters per second divided by meters per second, right? So it's just a numerical value. So the slower the medium, the larger the index is going to be, right? And the speed of light in a medium will never be faster than speed of light in a vacuum, which means this ratio can never be less than 1. In vacuum, it's going to be 1. In anything slower, it will be greater than 1. So here's a little chart. You can see, there we go, in a vacuum, it's exactly 1. In air, it's slightly greater than 1. Okay, light slows down a tiny little bit in air, but not much. So a lot of the problems we'll do today will assume that light's traveling through air, and then we'll assume its full speed of 3 × 10⁸ meters per second. But now look what happens when it goes into water or ethanol, glass, common glass, quartz, and even look at diamond, right? Diamond's one of the most dense materials that we know of. That light can still pass through, okay? So we say it's optically dense. The greater the optical density of a material, the slower light will travel through it. So if you look at diamond, it's, gosh, light slows down significantly, right, from what it does in a vacuum, okay? So when we say the speed of light is the speed limit of anything, that's only true in a vacuum, right? Light can travel quite a bit slower in other materials. Okay, let's get into some math here. This is the last part. I know that we understand the concept of refraction, and this is called Snell's law of refraction. Okay, so Snell was a physicist who did work in the area of light and optics, and here's what he came up with, right? So when we have a light ray that travels from one medium to the next, and it refracts or bends at that boundary, there is a mathematical relationship between the index of refraction for each of the materials and the angles, the incident angle and the refracted angle. Okay, so you kind of have to match up this diagram here with the equation that we have, right? So let me see if I can do this here. Get my pen going again. You never know where this thing's going to start. Let's get it going. There we go. Oh, okay, now it's working. All right, so here's our incident angle in 2. Now, really, in this case, doesn't matter, you know, which we call the incident, which we call the refracted angle, because we can plug them into either side of the equation. But we use the index of refraction and the angle in the same medium. Those have to be paired up together here, okay, when we use the formula. So notice up here, right, we have our index of refraction in material 2 and the angle in material 2. Okay, same thing on this side, right? The index of refraction in material 1 and the angle of refraction have to stay together when we use the formula. Okay, so here's the basic formula. We say the index of material 1 times the sine of angle in material 1 has to be equal to the index in material 2 times the sine of the angle in material 2. Okay, so simple equation. Yeah, we'll need a calculator here to find the sine of angles, but you guys can handle that just fine. And this is just a reminder down below here, right? What is in? It's the index of refraction. It's the ratio, right, of the speed of light in a vacuum divided by the speed of light in the medium or material. Okay, so let's see how this would apply in some examples here. Okay, so here we have light traveling from one material to another. We want to find the angle of refraction, okay? So the angle 1 up above. Now, before we even do this, can we tell which case do we have? Are we moving from slow to fast or fast to slow? Well, we can tell that by looking at the angle of refraction. Not the angle, I'm sorry, the index of refraction. So here's our N2 material, it's 1.5, right? And remember, 1 is basically the speed of light in a vacuum or air, very close to air. So 1.52 would tell us that this is the slower material, right? And this is the faster material. Okay, so if we used our pencil test, we should be able to tell right away that as our pencil travels from slow to fast, the ray should move away from the normal line. So we should expect to find an answer that is greater than 30 degrees. Okay, so we know this up here has to be greater than 30 degrees. Now, how much greater? That's where we've got to use Snell's formula. Okay, so let's go ahead and set that up here. And I need to clear that. All right, so here's Snell's formula. And let's first, since we're trying to solve for the angle, let's go ahead and get sine of angle 1 by itself, right? So to do that, we're just going to divide both sides by N1. So now we can plug in our numbers. In 2, we're going to put in 1.52. In 1 is 1, and then the sine of angle 30 degrees. Now, when you do this on your calculator, make sure you are in degree mode, right? Not radian mode, okay? But the rest really at this point is calculator work, okay? So we do all this, right? 1.52 divided by 1 is just simply 1.52 times the sine of 30 degrees, which is 0.5. So if we multiply those together, we get the sine of the angle equals 0.76. Now, we want to find the angle, which means we have to use arc sine or inverse sine on our calculator to do that, okay? So it would look like this, sine of -1 or inverse sine of 0.76. And if we let our calculator do that, it should give us the angle, right? So here's our angle, 49.6 degrees. Now, it matches what we had expected, right? We knew the angle had to be greater than 30 degrees, and it is. It's almost 50 degrees, so quite a bit of bending here as it refracted from a slow material to a fast material. Okay, so there's a example here. So let me clear this, and let's look at one more example. Okay. All right. So in this case, we know both the angles. We know one of the indices of refraction. We're being asked to find the other index. So I'm going to start with the same equation, but this time we're solving for N2. Get my pen going here. All right. So in this case, we want to solve for N2. So how do we do that? So first we're going to divide both sides by sine of the angle 2. And now we can plug in our numbers. So sine of 30 degrees in the top here is 0.5. Sine of 20 degrees is 0.34. And N1 is 1. So we just plug all that in. We don't need to take inverse sine because we're not finding the angle. In this case, we're finding one of the index of refraction. So let's just let the calculator do the work, and we get 1.46, okay? Now, if you get an answer less than 1, you've probably done something wrong, right? Because no material can have an index of less than 1. That would say it's traveling faster than the speed of light in a vacuum, right? That can't be the case. So this answer makes sense from that standpoint. What it tells us is we're still going from slower to faster material, and it should be moving away from the normal line, which is exactly what we see, right? We go from an angle of 20 degrees incident to 30 degrees refracted. Okay, so 2 examples where we get into the math here with refraction using Snell's formula. But using that formula, we'll always have to know 3 of the 4 variables, right? 2 indices, 2 angles. but we can be able to solve for any one of those four if we're given the other three, any one of the indices or any one of the angles of it. Okay. All right, let me clear this here. Didn't want to clear. Let's try it again. Why is this not going? All right. So that's it. Let's just review our objectives a little bit. The first thing we did was to explain the law of reflection, right? So angle in equals angle out. It's the best way to think about that. How do we locate the images formed by a plane mirror? Well, they're going to be on the opposite side of the mirror, but the same distance that the real object is in front of the mirror. And we can use light rays to kind of draw that out and see geometrically where it would form. And then the last, we understand the concept of refraction. It happens when we move between two media at different speeds. And we know the two cases, right? We're either going slow to fast or fast to slow. And how does that move the light ray either closer or further away from the normal line? And then we can use Snell's law and this concept of index of refraction to be able to numerically solve these problems. Okay, all right, so that's it for today. Let's go ahead and wrap this up here. There is an assignment in Google Classroom that goes with this lesson, Google form or quiz. So take a look at that, work through it, and we'll get together next week and talk about this. Thanks.